Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, this is the pilot episode of Financial Algebra. Okay, so this, it's not going to work. Let me try that there. Financial Algebra. This is the textbook we are going to use. It's just disappearing because of my background. Financial Algebra, second edition. Okay, so this is chapter 1.1, Discretionary and Essential Expenses. So I'm just going to do the examples from the chapter, and that's going to summarize the content within. So example 1 says, Elena knows that her morning cup of coffee is most definitely a discretionary expense. So let me stop right there and highlight that. Discretionary expense. Sorry, it's a little blurry on the left there. Didn't fit the scanner properly. All right, what is the difference between discretionary and essential? Well, essential expense, for example, would be food. We need to eat, okay? Can't live without food. So you go to the grocery store, you buy food. That is an essential expense. Discretionary expense is an expense that you don't need, okay? It's something that you want, not need. Here's a good example. This device, an Oculus, okay? I didn't need this. I wanted it. So you have to decide whether or not you want to spend money on discretionary, but you really kind of have no choice whether or not you're going to spend money on essential because it's essential. Okay, so let's carry on. She pays $2.75 for a 9-ounce cup of coffee. So I like to highlight the important components. Okay, so she's paying $2.75 for a 9-ounce cup. Okay. And she was wondering if that is typical price. So on Monday, she asked 6 of her coworkers. So there's another key component. She asked 6 of her coworkers what they paid for that same 9-ounce cup of coffee. Okay, their cost per cup were $2.85, $2.15, $1.95, $3, $2.05, and $2.40. How can Elena compare her expenses with those of her coworkers? Okay, so what she should do is use a comparison with the mean, the average of what her coworkers paid. So in order to do an average, what she would do is take all of these values, 2.85 plus 2.15 plus $1.95 plus $3 plus $2.05 plus $2.40. Okay, that would be the sum of all the values of the coffee. Okay, so those 6 people total paid this amount if you added it up. But to find the average, you then take all of those values and divide by the number. So there's 1, 2, 3, 4, 5, 6 coworkers, 6 cups of coffee, their prices divided by 6, and that would equal the mean. So in order to do this in the calculator, I'm going to take 2.85. Oh, and by the way, when you put it in the calculator, if you want to do it all at once, you need to put your numerator all in the parentheses and the denominator all in the parentheses. In this case, the denominator is just 6, so you don't need a parentheses around just a number 6. But I would need a parentheses around 2.85 plus 2.15 plus 1.95 plus 3 plus 2.05 plus 240. Okay, so I'm going to take all of those values, divide it by the number and hit enter. And I got 2.4. And since it's money, we round out to a hundredth position. So it's 2.40. So the average cost of a cup of coffee from her 6 coworkers was $2.40. Okay, so the mean is $2.40. Elena's expense is 35 cents above. She paid $2.75. So if you took that $2.75 and subtracted, you would get 35 cents. She paid 35 cents above the average of her 6 coworkers. So it sounds like she found an expensive coffee shop. Okay, so there's our introduction, our first example in the book, and it's on mean. All right, so mean, average. Okay, and there is going to be a symbol that we're going to use for the mean, and you use the letter X with a line over the top, and it's called X bar. That's how you read it when you're reading it. So the mean is X bar. Okay, example 2, sigma notation. So let's talk about this a little bit. So here's an X bar. So X bar. And remember what I said on the last page, that is the mean or the average. And it equals 1 over n. Well, n equals the number of elements in a set. Okay, so on this the last example, she asked 6 coworkers for the cup of coffee prices. So n would have equaled 6. Okay, so it'd be 1 over 6. And then this here is called sigma. It is a Greek letter. It is the capital sigma. There is also a lowercase sigma that looks something like that. Okay, and that's used for something else in math. But the capital sigma means, so capital sigma looks like this. And it means the sum of, and that's how you say it. So this would be X bar equals 1 over n times the sum of I equals 1 to n of X sub I. Okay, so we need to keep going. I is the number of in our element number. Let's call it that, the element number. So let me go back to the last page here. And so if in this order here, this would be element number 3. So that would be called X sub 3, for example. Okay. So the I is the element number, and X sub I is the number of, how would I say that? The number in a list. All the numbers in a list. So X sub I would be all of the numbers in a list. Okay. And now we're going to put this all together. So X bar is the sum, n is the number of elements in a set, and the sigma notation means the sum of. So what we're going to do is we're going to take I equals 1, the first element in the set, and go out to the last element in the set, in this case 6, X sub I, all the numbers in the list. So X sub 1, X sub 2, X sub 3, X sub 4, X sub 5, and X sub 6. And that tells us where to stop. This tells us where to start. So let me put this. Start. And this means where you stop in the set. We might not always use all of the set. You might want to take the first 10 out of 20 in a set. So you'd say I equals 1 to 10 instead of 1 to 20 when there's a total of 20. Okay, so example 2, now let's put this to work. Example 2 says use the information about coffee prices in example 1 to represent the formula for the mean price using a compact notation. So this is the compact notation here. So we want our problem to look like this. So that's all we're doing is we're putting this together. So solution says to examine the list of 6 coffee prices in example 1 the first amount, $2.85, can be symbolized by X sub 1. Okay. Likewise, X sub 2 represents the second number in the list, or $2.15. So if I go back, 285 is X sub 1, 215 is X sub 2, X sub 3, X sub 4, X sub 5, and X sub 6. Okay, get the idea? So likewise, okay, so I already read that. The list can then be represented as, and there's the 6. Okay, 285 is the first element, and so on, all the way out to the last or the 6th element. So we list them as just X sub 1 through X sub 6. And notice what I'm saying, sub. Okay, these are called subscripts. So if you've ever written a paper and you had to cite your work and you use this, it's called a subscript. So we just say X sub and then the number, and that's how you read it. So X sub 1, X sub 2, and so on. So the formula for the mean, X bar, of the coffee prices can be symbolized by the following. So I want this formula. So it's going to be X bar equals 1 over N. What does N mean? The number of elements in the set. How many elements do we have in our set? 6. So it's 1 over 6. And then the sigma logo, okay? And I equals our first element, 1, and we want to go out to the last one. We want to count them all. So N is going to become 6 up here. And this is going to be X sub I. Okay, so now instead of just writing this out, now we're going to solve it by filling in our givens. So we're going to then say that that is going to equal 1 over 6 times the quantity of all of these added up. That's what this means. The sum of X sub 1 all the way to X sub 6. So you would say X sub 1 plus X sub 2, forgot my 1, plus X sub 3 plus X sub 4 plus X sub 5 plus X sub 6. Okay, and when I do that, that is going to be the same as what we wrote on the previous page, which is all these numbers divided by 6, because 1/6 times a set of numbers is the same as that set of numbers divided by 6. 1 over 6 times the same as divided by. And we already did this, and we got it to be $2.40. Okay, so the mean coffee price is $2.40. Okay, here's example 3, and it says Anthony wants to make a discretionary purchase of a basic laptop computer. He checks the prices of a particular make and model listed by 7 different vendors on a shopping comparison website. He found these prices: $850, $798, $2,400, $790, $836, $700, and $780. He computes the mean as $1,022. The number doesn't seem to be a good representation of the data. How can he find a better representation? Okay, so let me highlight some stuff here. The mean as $1,022. Well, all of these prices are under $1,022 except for this one. This one is causing a problem. So if we were to graph this data, this one would be way out off the linear regression, if you will. Let me show you. Yeah, I was thinking about graphing that, but I changed my mind because it's not bivariate, so I'm not going to do that. But as you can see, 2,400 is way greater than the rest of them. It's way above the mean. So it's not a good representation. So in the prices Anthony found, there is an outlier. So that yellow one that I marked here is called an outlier. Okay, whenever we have a piece of data that does not fit, we call it an outlier. Okay, it's far away from the group. Okay. And that's when there is an outlier, the mean is often not a good representation. So when an outlier exists, we do not want to use the mean. Instead, we're going to use the median. And the median just means the middle value when you put the values in numerical order from least to greatest. Okay, so when the mean of the data set is not equal to the median, okay, so if the mean and the median are not equal, then the data is what's called skewed. Okay, so we have skewed data. If the mean does not equal the median, then the data is skewed. Okay, data is skewed. The median is unaffected by outliers. Okay, so let me just show you how we're going to represent this data. We are going to put it in an array, which means put it in order from least to greatest. So 700 was the cheapest computer and 2,400 was the most expensive, and these were the values in between. And when you do that and you have an odd number, so this is an example with an odd, when n is odd, the number of elements in your set. When it's odd, you just take the middle number when they're in order. So 1, 2, 3, 4, 5, 6, 7 pieces of data. 4 is in the middle, 3 on each side. This is our middle, and therefore that is our median. Okay. So outliers do not affect the median. For example, if I said this was 52,400 instead of 2,400, this median is still going to be 798. I could change this value to $7. Bargain Bernie has a computer for $7. The median didn't change, no matter how much the values change, as long as the order doesn't change. If you don't make any of the numbers on the left greater than your median, then the median will not change. Okay, so example 4 is now going to talk about something very similar. So it's a really quick example. It says, suppose that in example 3, Anthony had only found the first 6 laptop prices. So if I go back, if he only found the first 6 laptop prices, then $2,400 is not going to be there. Or they might be talking about this order here, 1, 2, 3, 4, 5, 6, and the $700 one is not there. But I'm thinking they're talking about the outlier here. But if we get rid of the outlier, we can use the mean. And they did not get rid of the outlier. They got rid of 1, 2, 3, 4, 5, 6. They didn't get rid of the 700. Which one did they get rid of for this example? 790, 798, 836, 780. They got rid of. Okay. So they actually eliminated 780. Not 2,400. Okay, so all we did was took this set of numbers and got rid of 780. So it's 700, 790, 798, 836, 850, 2,400, and here they are. Okay, so now we have an even number of data points. Okay. So as in example 3, we arrange the numbers in ascending order and then pair the numbers since there are an even number scores. Okay, so this is for an even scenario. Okay, so there are no numbers to the left alone in the middle that are left alone in the middle. There is no middle number in this case. Well, which one is it? 798 or 836? Well, when this happens, we take the mean of the middle 2 numbers. So you would take 798 plus 836 and divide it by 2. And that's going to equal 8 and 6 is 14, carry the 1, 9, 10, 11, 12, 13, carry the 1, 15 and 1 is 16 divided by 2, and that will equal 8, 1, Okay, so the median is $817. Again, notice that the number of scores below the median is the same as the number of scores above the median. Okay, so now that the median is 817, we have 3 scores below, or $3 values below, and 3 above. Okay, and the median is resistant to extreme scores, or in this case, dollar values. Okay, example 5 says a survey was conducted of 880 college students attending the same university. They were offered a list of 10 different internet service providers and were asked to select the one they prefer. So the question here is, can a service provider receiving only 89 votes out of 880 college students come out on top? In other words, could they win? You only have to win by 1 vote. Is that possible? So in this solution, it can be answered by determining the mode. In other words, which internet service provider got the most number of votes. That's the mode, okay? M-O-D-E, mode is most, frequent, okay? So the mode is often used with non-numerical variables, such as in a preference survey. A set can have no mode. If there are 2 modes, the set is called bimodal. Bi meaning 2, bimodal. If each of the 880 votes were split evenly among the 10 different internet service providers, each would get 88 votes and there would be no mode. Okay, so I have created this scenario with a graph. Okay, so here is a chart I made, and all these little Wi-Fi logos represent one internet company, service provider. So if you want to take the time and check, each of these have 44 in them. So 44 times 2 is 88. So this is one internet provider with 88 votes is what they're saying. So if I have 88 votes times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 companies, which I have down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, company 1 through 10, they all have 88 votes. There is no mode. They're all equal. This would be a 10-way tie. All right. In that case, there'd be no mode. But if there is only 2 modes, it would be called bimodal. Okay. So let me do something here. So this is what a bimodal set would look like. Okay. A set of data where they both have the same amount. That'd be bimodal. If I had another set that was different. Okay. Anyhow, these are all the same. So can a service provider, there's 88 in each of these, by the way. This one got 88 votes. This one got 88 votes. And so did this, and so on, and so on. Okay. They're all 88. And these 2 are as well, but I'm leaving that off for a reason. Okay. So can a service provider receiving only 89 votes come out on top? Well, what if I took this person and they decided that they did not want this company number 10, but they decided 9 was their favorite company. Now this one has 87 and this one has 89, and this is the mode, and therefore this service provider number 9 is the winner. Okay. So can a service provider receiving only 89 votes come out on top? And the answer is yes. You only need 1 vote above the average of all the others if it's all equal to win. Okay, example 6 says transportation expenses to and from work are considered essential expenses. Okay, so there's the other word finally brought to us. Okay, brought to you by the letter E, essential expenses. Okay, essential meaning it's necessary. Okay, transportation expenses. You can't make money if you don't go to work. And if you don't go to work, if you don't transport there, you can't get there to make the money. So it's essential. Okay. Charlie Jane, I almost said Charlie Chan. Charlie Jane would like to reduce this essential expense by biking to work rather than taking her car. She found 30 different ads, both online and in print, for the make and model of a bicycle she wants to purchase. She made a list of the prices in ascending order. Okay, so there's that ascending order thing again. Okay. Not all books mention what it's called, but it's called an array. All right, ascending order. So if, as you can see, 250, 250, 275. So I'm just going to circle these for now. There's two 250s, four 275s, one 280, two 290s. I'm out of colors. 1, 2, 3, 4, 5 310s. Let's go back to red now. No, they're right next to each other. Blue. Here's two 315s, and then four more 315s. Okay. Let me get rid of this little thing here. All right, and then there is one 320, three 325s, a 330, a 335, a 340, and finally, three 350s. Okay, so we just broke those up into their values. She wants to analyze the price, but is having trouble because there are so many numbers. How can she organize these prices in a helpful format? How can she organize these prices into a helpful format would sound better. Okay, so the first thing I would want to do is make a T-chart where one column is price, P in dollars, and the other one is the frequency, F, how many times that dollar amount occurred. So let's just go down the line here. 250 occurred twice, 275, 4, 280 once, 290 twice, 310 should be 5, 315 should be 6, okay, 315 is 6, 320 is 1, 325 should be 3, 330 is 1, 335 is 1, 340 is 1, and 350 is 3. Okay, so we've listed them all. Then what you do is you take the total, add this column up, 30 bicycles. These are the prices of individual bicycles, okay? And so that's how we can put this list into a helpful format. And that's it, just a T-chart, a frequency table. Okay, example 7 says, find the mean. Find the mean of the bicycle prices from example 6. So I brought this table over from example 6. It's the same table, same value, same frequency. It is a frequency table. And how in the world are we going to find the average price? Well, we can't just add all of these up and divide by 30, or not 30. There's only how many? 12. I can't take all of these and divide them by 12 because that doesn't take into consideration the number of bicycles at those prices. So you add a bicycle at 315 and the average was 320, that would reduce the average because it's below average. Okay, a price, if I added another bicycle to 350, then the average was 320, the average would increase because you add a number above the average and the average will increase. So what we need to do is find the product of a price of one bike and multiply it by how many bikes that we got. And that's what we're doing here. So then we're going to do the product of P times F. So we're going to take 250 times 2 is 500, 275 times 4 is 1,100, and so on, and so on, and so on. Okay, you add all of those up, and you total the product of the two. Okay. So then what we need to do, so the sum of those 12 bicycles, not 12 bicycles, 30 bicycles with 12 different prices, the sum of those 30 bicycles was $9,250. So then what you would do just to find the mean now, the mean is very simple. The total price was $9,250 and you have 30 bicycles. So you just divide, get rid of those zeros. 3 goes into 9 3 times. 3 does not go into 2. 8 times 3 is 24, and with a remainder of 1. So 3 goes into 10 3 times with a remainder of 1. So it repeats 308 33 3333. Since it's dollars, we'll round to 2 decimal places. And the average price of these 30 bicycles is $308.33. Okay. So price times frequency and add up all those products.